Hi. In the previous lectures of topic number 8, we covered the small signal model of all the non-isolated PWM converters operating in CCM and DCM, but we need extend that result to the isolated converters, the PWM converters where the transformer is inserted for the galvanic isolation and the other purposes. So first, let me review the content of the previous lecture about the DCM dynamics of PWM converters. Its result is applicable to non-isolated converters, and also it can be applied all the PWM converters, isolated PWM converters too. Okay, so we assumed that we have some converter, PWM converter. It really doesn't matter whether isolated or non-isolated. Okay, suppose the compensation voltage feedback circuit is designed assuming the CCM operation and converter is jumped into DCM operation for some reason. Then this is the variation that will occur in the dynamics of a converter. So during the CCM operation, this is the utilization output transfer function. So this double pole will be split into two real poles. One is here, another one is here. So we have this significant reduction in the magnitude of open loop transfer functions that will be reflected to this loop gain of the converter, and the reduction in the loop gain magnitude will be reflected as the boost increase of this the low frequency value of output impedance of a converter. Okay, so same thing will occur to audio susceptibility. Okay, but the stability margin will remain the same or even increased. Of course, the crossover frequency of the loop gain will be reduced this much. Okay, and the change in the output impedance is directly reflected to the change in the step load response. Suppose this is the step load response in CCM. So in CCM, we have this kind of characteristics. So this is our voltage with some ripple, and it due to this transient step transient in the load current. So it goes up and it shows the first order characteristics very fast and return to the original value. And there is another step change and it goes down and grow. Okay, so this result is basically first order system one. And this is very fast, and this overshoot and this undershoot will be very small. Okay, so the reason for that is if you take a look at this is the closed loop output impedance of converter in CCM. Then this is the differentiation, and there is only one pole here approximately. So that pole occurs at high frequencies, so it shows fast response here. Okay, so now this converter went into the DCM operation, then output impedance will be changed like this. This is a closed loop output impedance, and it has larger value, and this is double pole. So double pole shows some oscillatory behavior, and due to this double pole and this larger value in the magnitude, the DCM trend response shows like this. This is a characteristic of this second order system, and maybe it can go down and go up something like this, or just it goes one resonant type peaking here and another dipping here. Okay, so this magnitude will be large. All right, and this time constant is very slow compared to this CCM counterpart, because the double pole is located here, and previously for the CCM case, pole was here, and this is much lower in frequency and show the slow response, and the larger value of this will show larger overshoot and undershoot. Okay, so this can be problem. So this can be problem when converter operating in DCM, all right? But this can be fixed by modifying the control scheme. What I was talking about here is I was assuming the voltage mode control. Maybe we'll discuss the details about voltage mode control in the next topic, and the conventional control adapting only one feedback from the out voltage is called voltage mode control. And this is the inherent limitation of the voltage mode control, and this can be fixed by using the current mode control. Current mode control employs another control from the inductor current on the top of existing out voltage control that is called current mode control or two-loop control. And current mode control deserves a rigorous analysis, and that will be discussed in the next topic. And so we can improve this, we can eliminate or alleviate this problem using another control scheme called current mode control. That is one biggest motivation of using current mode control. So, but we are assuming voltage mode control, and we'll discuss voltage mode control first, and we'll talk about the current mode control. Okay. Now most people, they are using the current mode control, and the very small portion of people is paying attention on the voltage mode control. But voltage mode control is also important because all the theory about this dynamics and control of PWM converter evolved around the voltage mode control. Okay, so there are many good results are generated from the voltage mode control, and most of them can be still applicable to the current mode control with some minor modification. So it is very important to thoroughly understand the voltage mode control before attempting to study the current mode control. Okay, so that topic will be covered in the next topic. Topic number 9 and number 10. All right. Okay. As I said, our interest was the not isolate converter in the CCM or DCM, and only with the voltage mode control. Okay. Now we need to extend that result to this non-isolated converters. So this is one example. This is the Ford converter. So this we have this. This is the magnetizing inductance of this 3-winding transformer. So this is the transformer, first winding, second winding, and another winding, tertiary winding is here. And the purpose of this tertiary winding is, and this diode, this is called the reset diode. Their sole purpose is to guarantee the peaceful reset of this magnetizing inductance. Okay, so during the operation, this can be ignored for the dynamic analysis. So all of this can be ignored because they interfere only with the reset mechanism of this magnetizing inductance. So this part will be gone. Then you have a transformer. This is isolation transformer, and this is ideal transformer because this magnetizing inductance is took out here. Okay, and you have 2 diodes and 1 switch. Okay, so this switch and this diode, they are located in distance with transformer isolation. So the SPDT switch structure is not apparent here, but if you understand the operation of this converter, this combination of this active switch and 2 passive diodes, all of them are considered as one SPDT switch. With the function of this, you generate this rectangular waveform here. So the voltage at the input port of this low-pass filter is simply this one. This is the same as the buck converter case, and this low-pass filter will average this and generate this mean value of this as the output of this converter. Okay. So in terms of its function, we just ignore this and we consider this ideal transformer, and there is one PWM switch. Okay. This kind of concept is applicable to all the transformer isolated converter. So maybe we combine this, and we derive the small signal model of this transformer combined with this PWM switch. Okay, so details about this will be covered in the following lecture, in the following lecture slide. I'm showing the just result of that. Okay, so this is the PWM switch model in CCM. Okay, and this is for the non-isolate converter. So we have isolation. So only this transformer, and we have a transformer in PWM switch model. We merge two transformers, okay, and the only difference is change in this turns ratio of this ideal transformer. So it is 1 to ND, okay. N is coming here, D is coming here from the PWM switch, okay. And we have NIL here, okay. IL is here because we have this turns ratio, N is coming here. Okay, so everything remains the same, all right? And only you modify this turns ratio of ideal transformer and you put N here. Maybe this is called weighted PWM switch model. So this is the small signal model of Ford converter, and all the isolated converters, small signal model of them will be derived, can be derived in the manner similar to this, okay? So very straightforward. All right. So maybe some student, they know the small signal model of non-isolated converter, but they are having some trouble with non-isolated converter. That is not the case. Basically, they are the same. Okay. You only need to do it just the modification of this, okay, and some other things. Okay, for some circuit variables. All right. Okay. So let's go to the next step. Now you have a new topic of modeling for the converters and other converters. And the background behind this topic is we developed a small signal model of 3 basic converters in CCM and DCM. So basically, that job is done. And then what about the isolated converters? That is the big question. All right? Somebody said, your story is good only for the 3 converters, and you don't have nothing about the other converters. That is not true. Okay, so there are 3 basic converters, and by adding the transformer in between, somewhere in the non-isolated converter, you have isolated converter. Okay, so in every isolated converter, it has many switches and many diodes. Okay. So the structure of PWM switch is not apparent. But in non-isolated converter, the structure of PWM converter is obvious. It is there, so you just replace it. But in this converter, situation is a little bit different. There are many switches, many diodes, and they are located in distance with transformer isolation. Okay. But if you take a look at, if you think about the operational principle, and there is only one equivalent PWM switch in each converter, okay? Every single isolated converter, there is only one PWM switch, okay? That function is distributed among the many switches and many diodes, okay? So this one, and this for the converter, and small signal model, this converter is derived from the buck converter, okay? Then there are many buck derived converters. Their small signal model is almost identical with extremely minor modification, those of buck converter, because they are derived from buck converter, they are buck converter family, okay? Flyback converter is derived from the buck boost converter. So you know the small signal model of a buck boost converter, then you should know the small signal model of a flyback converter. Okay? So I'll explain this kind of concept. So this is called the tertiary winding reset for the converter. And this part is called the reset circuit. It only involves with resetting the transformer, this transformer. Okay? So it can be ignored. It does not interfere with dynamics of this converter, so it can be removed, omitted, okay? And there's a transformer, and transformer is a transformer, 1 to N transformer, and there are switch and two diode. Okay, but in terms of each function, if you understand this, if you analyze this, the basic function of this buck-derived converter is there is DC voltage, and in between there is a transformer. So input voltage is stepped up, and there is one PWM switch, and they generate this kind of waveforms. Okay, it alternates from NVS. This is a turns ratio of this transformer. This is a 1:1. Then this is VS. This is a voltage across VF. Then this becomes the same as the buck converter. Okay. So if you have this kind of waveform here, you understand this. Then this whole thing can be replaced with this transformer and PWM switch. Okay. This will generate the same waveforms at the input port of this low pass filter. And low pass filter is just filtering out to obtain the average value of this, and average value of this becomes the out voltage. Okay. So this is a PWM switch, and PWM switch is replaced with average model of PWM switch, which is ideal transformer, and there are two ideal transformers. They merged together to have this. Okay. Then turns ratio of this is just multiplication of turns ratio of this two individual transformer. Okay. This is very trivial to prove equivalence between this combination and this. Okay. Then you have this, right? Then everything becomes clear. Okay. All right. So I draw this when you are seeing some waveform in here. Then just think of this. Then replace with the PWM switch. You should consider this transformer. So it's very trivial modification, and this is averaged model. Is the same thing. Okay, I copied here. Then average equation of this is same as the conventional buck converter with turns ratio here. Okay, previously it was 1 to D. Now it's 1 to ND. So ND is coming here. This is constant, but this is what? Time varying function. Then you linearize this. You use the same procedure. Okay, then you have this. This is the small signal equation of this for the converter. And then you replace this with this PWM switch. Okay, only difference is this one. ND is here, and it was IL, and you have N here because of this. All right, everything remains the same. Okay, this is valid for any type of for the converter. There are many variation of this converter. Two switch for the converter, RCD reset for the converter, active clamp for the converter. So many converters. This is true. Okay, and this step can be applied other converters. So this full bridge converter, okay, you know the operation of this, but it really doesn't matter. You don't have to know every details about this, but eventually the voltage across this input port of low pass filter will be this, something like this, not something, exactly this one, and this average value is the output of this. Then if you see this, think about this, okay, then this is the small signal model. Everything remains the same. This N is coming here, okay, because N is here. It's a small signal model of full bridge converter and half bridge converter. Half bridge converter, this works as the voltage divider. So this is the same as you have two voltage source, half the VS here, half the VS here. Okay, remain the same, and you only have a factor of 2 here. Okay, here and here. It's obvious. Okay, so also if you analyze this, the voltage here is this one, and this is the replaced with PWM switch. Okay, this is a final example, and this can be applied to the older isolated converters derived from the boost converter and the buck boost converter. So now you have a small signal model of all the PWM converters. this is example of flyback converter. This is the flyback converter. Okay. Maybe you know some details about this. Okay, but it really doesn't matter. Just follow me. Okay. So you have LM here, and you have VS, and this is inverted. What I mean is dot. Usually dot is here, then another dot is usually here, but this one is here. This is the configuration of flyback converter. Then you reflect this side of this secondary winding, secondary side of this ideal transformer, inverted 1-to-n ideal transformer. Then Rm becomes n squared Rm, and this becomes NVS. This polarity is inverted because one dot is here, the other dot is here. Okay, so this is the same circuit. All right. Then you swap this voltage, and this voltage, and reverse the direction of the diode. Okay, reversal of polarity of this voltage, and the reversal of diode location, diode direction, they remain the same. Okay, you can prove that, or it's obvious. Okay, so this is the same circuit. Now we have this one. This is scaled. Originally it was Rm. Rm is magnetizing of this transformer, and this transformer magnetizing inductance is used as the functional transformer in flyback converter. There is the special case. Okay, there is scaled. Okay, scaling factor is this one, and the scaling factor is this one. So now you have this circuit, and the switch is here. You move switch to here. It's the same thing, right? Then this is what? This is the buck boost converter, equivalent buck boost converter. If you have flyback converter, this is the same equivalent buck boost converter, and you know small signal model of this. Okay, so I summarize the modeling process. This original flyback converter, and this is the equivalent buck boost converter. You know this. It's just scale this and change the direction of this and polarity of this and move this location here. Then this is what? This is small signal model of buck boost converter, which is small signal model of flyback converter. Okay, just look at this. This is just the scaling of VS hat and scaling of Rm. Okay, this is the inductor of this buck boost converter. Its origin is the magnetizing inductance of transformer. So we are using magnetizing inductance of transformer as the functional inductor. Okay. So this is very cheap. This flyback converter is L is missing. This is one. All right, not this one. The original one. You have this is one transformer. This provides the isolation, and it has this inductor in it. So this works as the inductor here. So this is very cheap. Okay, very popular in industries, and about the 95% of the power supply in your home electronics is flyback converter because they are cheap. Okay, all done, right? Okay, this is the